Welcome back. So we had a busy lesson last week, and I was really thrilled to see actually one of our master's students here at USF actually took what we learnt with structured deep learning and turned it into a blog post, which, as I suspected, has been incredibly popular because it's just something people didn't know about. And so it actually ended up getting picked up by the Towards Data Science publication, which I quite like actually. If you're interested in keeping up with what's going on in data science, it's quite good medium publication. And so Kerem talked about structured deep learning and basically introduced the basic ideas that we learned about last week, and it got picked up quite widely. One of the things I was pleased to see, actually, Sebastian Ruder, who actually mentioned in last week's class as being one of my favorite researchers, tweeted it, and then somebody from Stitch Fix said, "Oh yeah, we've actually been doing that for ages," which is kind of cute. I kind of know that this is happening in industry a lot, and I've been telling people this is happening in industry a lot, but nobody's been talking about it. And now that Karen's kind of published a blog saying, "Hey, check out this cool thing," and now Stitch Fix is like, "Yeah, we're doing that already." So that's been great, great to see, and I think there's still a lot more that can be dug into with this structured deep learning stuff. To build on top of Kerem's post would be to maybe like experiment with some different data sets, maybe find some old Kaggle competitions and see like, are there some competitions that you could now win with this, or some which doesn't work for would be equally interesting. And also like just experimenting a bit with different amounts of dropout, different layer sizes, because nobody much has written about this. I don't think there's been any blog posts about this before that I've seen anywhere. There's a lot of unexplored territory. So I think there's a lot we could build on top of here. And there's definitely a lot of interest. I saw one person on Twitter saying, "This is what I've been looking for ages." Another thing which I was pleased to see is Nikhil, who we saw his cricket versus baseball predictor as well as his currency predictor after lesson 1, went on to download something a bit bigger, which was to download a couple of hundred of images of actors, and he manually went through and checked which. Well, I think first of all he used Google to try and find ones with glasses and ones without. Then he manually went through and checked that they had been put in the right spot. And this is a good example of one where vanilla ResNet didn't do so well with just the last layer. And so what Nikhil did was he went through and tried unfreezing the layers and using differential learning rates and got up to 100% accuracy. And the thing I like about these things that Nikhil is doing is the way he's not downloading a Kaggle data set. He's like deciding on a problem that he's going to try and solve. He's going from scratch from Google. And he's actually got a link here even to a suggested way to help you download images from Google. So I think this is great. And I actually gave a talk just this afternoon at Singularity University to an executive team of one of the world's largest telecommunications companies, and I actually showed them this post because the folks there were telling me that all the vendors that come to them tell them they need like millions of images and huge data centers full of hardware, and they have to buy special software that only these vendors can provide. And I said, actually, this person's been doing our course for 3 weeks now, and look at what he's just done with a computer that costs him 60 cents an hour. And they were so happy to hear that, okay, this actually is in the reach of normal people. I'm assuming Nikhil's a normal person. I haven't actually met him. If you're proudly abnormal, Nikhil, I apologize. I actually went and had a look at his cricket classifier, and I was really pleased to see that his code actually is the exact same code that we used in lesson 1. I was hoping that would be the case. The only thing he changed was the number of epochs, I guess. So this idea that we can take those 4 lines of code and reuse it to do other things, it's definitely turns out to be true. And so these are good things to show, at your organization, if you're anything like the executives at this big company I spoke to today, there'll be a certain amount of not just surprise, but almost pushback of if this was true, somebody, you know, they basically said, if this was true, somebody would have told us so. Like, why isn't everybody doing this already? So, like, I think you might have to actually show them. You know, maybe you can build your own with some internal data you've got at work or something, and be like, oh, here it is. You know, didn't cost me anything. It's all finished. Vitally, I don't know how to pronounce his name correctly, has done another very nice post on just an introductory post on how we train neural networks. And I wanted to point this one out as being like, I think this is one of the participants in this course who's just got a particular knack for technical communication. And I think we can all learn from, you know, from his posts about good technical writing. What I really like particularly is that he assumes almost nothing. Like, he has a kind of a very chatty tone and describes everything, but he also assumes that the reader is intelligent. But, you know, so like he's not afraid to kind of say, here's a paper or here's an equation or whatever, but then he's going to go through and tell you exactly what that equation means. So it's kind of like this nice mix of like writing for respectfully for an intelligent audience, but also not assuming any particular background knowledge. So then I made the mistake earlier this week of posting a picture of my first placing on the Kaggle Seedlings competition, at which point 5 other FastAI students posted their pictures of them passing me over the next few days. So this is the current leaderboard for the Kaggle Plant Seedlings competition. I believe the top 6 are all FastAI students, or in the worst of those, teachers. And so I think this is like a really... oh, look, James has just passed. He was first. This is a really good example of like what you can do. You know, this is, I'm trying to think. It was like a small number of thousands of images. And most of the images were less than 100 pixels by 100 pixels. And yet we, you know, I bet my approach was basically to say, let's just run through the notebook we have. Pretty much default took me, I don't know, an hour. And I think the other students are doing a little bit more than that, but not a hell of a lot more. And basically what this is saying is, yeah, these techniques work pretty reliably to a point where people that aren't using the FastAI libraries are, you know, literally really struggling. I suspect all of these are FastAI students. You might have to go down quite a way. So I thought that was very interesting and really, really cool. So today we're going to start what I would kind of call like the second half of this course. So the first half of this course has been like getting through, like these are the applications that we can use this for. Here's kind of the code you have to write. Here's a fairly high-level-ish description of what it's doing, and we're kind of done for that bit. And what we're now going to do is go in reverse. We're going to go back over all of those exact same things again, but this time we're going to dig into the detail of every one, and we're going to look inside the source code of the FastAI library to see what it's doing and try to replicate that. So, in a sense, like, there's not going to be a lot more best practices to show you. Like, I've kind of shown you the best practices I know, but I feel like for us to now build on top of those, to debug those models, to come back to part 2, where we're going to kind of try out some new things, you know, it really helps to understand what's going on behind the scenes. Okay, so the goal here today is we're going to try and create a pretty effective collaborative filtering model, almost entirely from scratch. So we'll use PyTorch as a automatic differentiation tool and as a GPU programming tool and not very much else. We'll try not to use its neural net features. We'll try not to use FastAI library any more than necessary. So that's the goal. So let's go back and, you know, we only very quickly looked at collaborative filtering last time. So let's go back and have a look at collaborative filtering. And so we're going to look at this movie lens data set. So the movie lens data set basically is a list of ratings. It's got a bunch of different users that are represented by some ID, and a bunch of movies that are represented by some ID, and a rating. It also has a timestamp. I haven't actually ever tried to use this. I guess this is just like what time did that person rate that movie. So that's all we're going to use for modeling, is 3 columns: user ID, movie ID, and rating. And so thinking of that in kind of structured data terms, user ID and movie ID would be categorical variables. We have 2 of them, and rating would be a dependent variable. We're not going to use this for modeling, but we can use it for looking at stuff later. We can grab a list of the names of the movies as well. And you could use this genre information. I haven't tried to. Be interested if during the week anybody tries it and finds it helpful. My guess is you might not find it helpful. We'll see. So in order to kind of look at this better, I just grabbed the users that have watched the most movies and the movies that have been the most watched, and made a crosstab of it, right? So this is exactly the same data, but it's a subset. And now rather than being user movie rating, we've got user movie rating. And so some users haven't watched some of these movies. That's why some of these are not a number. Okay. Then I copied that into Excel. And you'll see there's a thing called collabfilter.xls. If you don't see it there now, I'll make sure I've got it there by tomorrow. And here is where I've copied that table. Okay, so as I go through this like setup of the problem and kind of how it's described and stuff, if you're ever feeling lost, feel free to ask either directly or through the forum. If you ask through the forum and somebody answers there, I won't need to answer it here. But if somebody else asks a question you would like answered, of course, just like it, and Yannet will keep an eye out for that. Because kind of as we're digging in to the details of what's going on behind the scenes, it's kind of important that at each stage you feel like, okay, I can see what's going on. Okay. Okay. So we're actually not going to build a neural net to start with. Instead, we're going to do something called a matrix factorization. The reason we're not going to build a neural net to start with is that it so happens there's a really, really simple kind of way of solving these kinds of problems, which I'm going to show you. And so if I scroll down, I've basically, what I've got here is the same thing, but this time these are my predictions rather than my actuals. And I'm going to show you how I created these predictions. Okay, so here are my actuals, right? Here are my predictions. And then down here, we have our score, which is the sum of the difference squared, average, square root. Okay, so this is RMSE down here. Okay, so on average, our randomly initialized model is out by 2.8. So let me show you what this model is. And I'm going to show you by saying, how do we guess how much user ID number 14 likes movie ID number 27? And the prediction here, this is just, at this stage, this is still random, is 0.91. So how are we calculating 0.91? And the answer is, we're taking it as this vector here dot product with this vector here. So dot product means 0.71 times 0.19 plus 0.81 times 0.63 plus 0.74 plus 0.31 and so forth. And in linear algebra speak, because one of them is a column and one of them is a row, this is the same as a matrix product. So you can see here I've used the Excel function matrix multiply. And that's my prediction. Having said that, if the original rating doesn't exist at all, then I'm just going to set this to 0, right? Because there's no error in predicting something that hasn't happened. Okay. So what I'm going to do is I'm basically going to say, all right, every one of my my predictions is not going to be a neural net. It's going to be a single matrix multiplication. Right. Now the matrix multiplication that it's doing is basically, in practice, is between this matrix and this matrix, right? So each one of these is a single part of that, right? So I randomly initialize these. These are just random numbers that I've just pasted in here. So I've basically started off with two random matrices, and I've said, let's assume for the time being that every rating can be represented as the matrix product of those two. So then in Excel, you can actually do gradient descent. You have to go to your options, to the add-in section, and check the box to say turn it on. And once you do, you'll see there's something there called solver. And if I go solver, it says, okay, what's your objective function? And you just choose the cell. So in this case, we chose the cell that contains our root mean squared error. And then it says, okay, what do you want to change? And you can see here we've selected this matrix and this matrix. And so it's going to do a gradient descent for us by changing these matrices to try and, in this case, minimize, because it says minimize this Excel cell, right? GRG nonlinear is a gradient descent method. So I'll say solve, and you'll see it starts at 2.8, and then down here you'll see that number's going down. Right? It's not actually showing us what it's doing, but we can see that the number's going down. So this has kind of got a neural netty feel to it, in that we're doing like a matrix product and we're doing a gradient descent, but we don't have a non-linear layer and we don't have a second linear layer on top of that. So we don't get to call this deep learning. So things where people do like deep learning-ish things, where they have kind of matrix products and gradient descents, but it's not deep, people tend to just call that shallow learning. Okay, so we're doing shallow learning here. Right, so I'm just going to go ahead and press escape to stop it because I'm sick of waiting. And so you can see we've now got down to the 0.39. All right, so for example, it guessed that movie 72 movie 27 for user 72 would get 4.44 rating. 27, 72, it actually got a 4 rating. So you can see like it's doing something quite useful. So why is it doing something quite useful? I mean, something to note here is the number of things we're trying to predict here is, there's 225 of them, right? And the number of things we're using to predict is that times 2, so 150 of them. So it's not like we can just exactly fit. We actually have to do some kind of machine learning here. So basically what this is saying is that there does seem to be some way of making predictions in this way. And so for those of you that have done some linear algebra, this is actually a matrix decomposition. Normally in linear algebra you would do this using an analytical technique or using some techniques that are specifically designed for this purpose. But the nice thing is that we can use gradient descent to solve pretty much everything, including this. I don't like to so much think of it from a linear algebra point of view, though. I like to think of it from an intuitive point of view, which is this. Let's say movie ID 27 is Lord of the Rings Part 1. And let's say and so let's say we're trying to make that prediction for user 72. Are they going to like Lord of the Rings Part 1? And so conceptually, that particular movie, maybe there's 5 numbers here. And we could say like, well, what if the first one was like, how much is it sci-fi and fantasy? And the second one is like, how recent a movie and how much special effects is there, you know? And the one at the top might be like, how dialogue driven is it? Right? Like, let's say those kind of these 5 numbers represented particular things about the movie. And so if that was the case, then we could have the same 5 numbers for the user saying like, okay, how much does the user like sci-fi and fantasy? How much does the user like modern, modern CGI-driven movies? How much does this user like dialogue-driven movies? And so if you then took that cross product, you would expect to have a good model, right? You would expect to have a reasonable rating. Now, the problem is we don't have this information for each user. We don't have the information for each movie. So we're just going to like assume that this is a reasonable kind of way of thinking about this system, and let's stochastic gradient descent try and find these numbers, right? So in other words, these factors, we call these things factors. These factors, and we call them factors because you can multiply them together to create this, right? They're factors in a linear algebra sense. These factors, we call them latent factors because they're not actually. This is not actually a vector that we've like named and understood and like entered in manually. We've kind of assumed that we can think of movie ratings this way. We've assumed that we can think of them as a dot product of some particular features about a movie and some particular features of to look what users like those kinds of movies, right? And then we've used gradient descent to just say, okay, try and find some numbers that work. So that's basically the technique, right? And it's kind of, the entirety is in this spreadsheet, right? So that is collaborative filtering using what we call probabilistic matrix factorization. And as you can see, the whole thing is easy to do in an Excel spreadsheet, and the entirety of it really is this single thing, which is a single matrix multiplication, plus randomly initializing.
Jeremy, we would like to know if it would be better to cap this to 0 and 5 maybe,
yeah,
so that
no
you don't
question.
get... Yeah.
And we're going to do that later, right? There's a whole lot of stuff we can do to improve this. This is like our simplest possible starting point, right? So what we're going to do now is we're going to try and implement this in Python and run it on the whole data set.
Another question is, how do you figure out how many... how it's clear how long are the metrics.
Yeah. Why is this 5?
Yeah.
Yeah. So something to think about, given that this is like movie 49, right? And we're looking at a rating for movie 49. Think about this. This is actually an embedding matrix. And so this length is actually the size of the embedding matrix. I'm not saying this is an analogy, I'm saying it literally. This is literally an embedding matrix. We could have a one-hot encoding where 72, where a 1 is in the 72nd position, and so we'd like look it up and it would return this list of 5 numbers. So the question is actually, how do we decide on the dimensionality of our embedding vectors? And the answer to that question is, we have no idea. We have to try a few things and see what works. The underlying concept is you need to pick an embedding dimensionality which is enough to reflect the kind of true complexity of this causal system, but not so big that you have too many parameters that it could take forever to run, or even with regularization it might overfit.
So what does it mean when the factor is negative then?
The factor being negative in the movie case would mean like this is not dialogue driven. In fact, it's like the opposite. Dialogue here is terrible. A negative for the user would be like, I actually dislike modern CGI movies.
So it's not from 0 to whatever. It's the range of score would be negative. Is there a range of score even? Like
no
maximum?
No, there's no constraints at all here.
Okay.
These are just standard embedding matrices.
Thanks. I have a couple of questions. So first question is, why can we trust these embeddings? Because like if you take a number 6, it can be expressed as 1 into 6, or like 6 into 1, or 2 into 3, and 3 into 2.
Oh, so are you saying like we could like reorder these 5 numbers in some other different order?
Or like the value itself might be different, as long as the product is something same.
Well, but you see, we're using gradient descent to find the best numbers. So like once we've found a good minimum, the idea is like, yeah, there are other numbers, but they don't give you as good an objective value.
Okay.
And of course, we should be checking that on a validation set, really, which we'll be doing in the Python version.
Okay. And the second question is, when we have a new movie or a new user, do we have to retrain the model?
That is a really good question, and there isn't a straightforward answer to that. Time permitting, we'll come back to it. But basically, you would need to have like a kind of a new user model or a new movie model that you would use initially. And then over time, yes, you would then have to retrain the model. So like, I don't know if they still do it, but Netflix used to have this thing that when you were first onboarded onto Netflix, it would say like, what movies do you like? And you'd have to go through and like say a bunch of movies you like, and it would then like train its model.
Could you just find the nearest movie to the movie that you're trying to the new movie that you're trying to add, and then?
Yeah, you could use nearest neighbors for sure. But the thing is, initially, at least in this case, we have no columns to describe a movie. So if you had something about like the movie's genre or release date, who was in it or something, you could have some kind of non-collaborative filtering model. And that was kind of what I meant by like a new movie model. You'd have to have some kind of predictors. Okay, so a lot of this is going to look familiar. And the way I'm going to do this is, again, is kind of this top-down approach. We're going to start using a few features of PyTorch and FastAI, and gradually we're going to redo it a few times in a few different ways, kind of doing a little bit deeper each time. Regardless, we do need a validation set. So we can use our standard cross-validation indexes approach to grab a random set of IDs. This is something called weight decay, which we'll talk about later in the course. For those of you that have done some machine learning, it's L2 regularization, basically. And this is where we choose how big a embedding matrix do we want. Okay. So again, here's where we get our model data. Object from CSV, passing in that ratings file, which remember looks like that. Okay, so you'll see like stuff tends to look pretty familiar after a while. And then you just have to pass in what are your rows effectively, what are your columns effectively, and what are your values effectively, right? So any collaborative filtering recommendation system approach, there's basically a concept of like, a user and an item. Now they might not be users and items, like if you're doing that Ecuadorian groceries competition, there are stores and items, and you're trying to predict how many things are you going to sell at this store of this type, right? But generally speaking, just this idea of like you've got a couple of kind of high cardinality categorical variables and something that you're measuring, and you're kind of conceptualizing it as saying, okay, we could predict the rating, we can predict the value by doing this dot product. Interestingly, and this is kind of relevant to that last question or suggestion, an identical way to think about this or to express this is to say, when we're deciding whether user 72 will like movie 27, it's basically saying which other users liked movies that 72 liked, and which other movies were liked by people like user 72. It turns out that these are basically two ways of saying the exact same thing. So basically what collaborative filtering is doing, kind of conceptually, is to say, okay, this movie and this user, which other movies are similar to it in terms of like similar people enjoyed them, and which people are similar to this person based on people that like the same kind of movies. So that's kind of the underlying structure. At any time there's an underlying structure like this, that kind of collaborative filtering approach is likely to be useful. Okay, so so there's basically two parts, the two bits of your thing that you're factoring, and then the value, the dependent variable. So as per usual, we can take our model data and ask for a learner from it, and we need to tell it what size embedding matrix to use, what validation set indexes to use, what batch size to use, and what optimizer to use. And we're going to be talking more about optimizers shortly. We won't do atom today, but we'll do atom next week or the week after. And then we can go ahead and say fit. All right, and it all looks pretty similar. It's to usual. Interestingly, I only had to do 3 epochs. Like this kind of model seemed to train super quickly. You can use the learning rate finder as per usual. All the stuff you're familiar with will work fine. And that was it. So this took, about 2 seconds to train. There's no pre-trained anythings here. This is from random, from scratch, right? So this is our validation set, and we can compare it. This is a mean squared error, not a root mean squared error, so we can take the square root. So that last time I ran it, it was 0.776, and that's 0.88. And there's some benchmarks available for this data set. And when I scrolled through and found the best benchmark I could find here from this recommendation system specific library, they had 0.91. So we've got a better loss in 2 seconds already. So that's good. So that's basically how you can do collaborative filtering with the FastAI library without thinking too much. Right. So now we're going to dig in and try and rebuild that. We'll try and get to the point that we're getting something around 0.77, 0.78 from scratch. But if you want to do this yourself at home, without worrying about the detail, that's, those 3 lines of code is all you need. Okay, so we can get the predictions in the usual way, and, we could, for example, plot, SNS is Seaborn. Seaborn's a really great plotting library. It sits on top of Matplotlib. It actually leverages Matplotlib. So anything you learn about Matplotlib will help you with Seaborn. It's got a few nice little plots, like this joint plot. Here is I'm doing predictions against actuals. So these are my actuals, these are my predictions, and you can kind of see the shape here is that as we predict higher numbers, they actually are higher numbers, and you can also see the histogram of the predictions and a histogram of the actuals. So I was just kind of plotting that just to show you another interesting visualization.
Could you please explain the n factors, why it's set to 50?
It's set to 50 because I tried a few things and it seemed to work. That's all.
What does it mean by that?
It's the dimensionality of the embedding matrix. Or to think of it in another way, it's like how, rather than being 5, it's 50.
Jeremy, I have a question about, suppose that your recommendation system is more implicit, so you have zeros or ones instead of just actual numbers.
Right. So basically we would then need to use a classifier instead of a regressor.
You have to sample the negative or something like that. So if you just have ones, let's say, like just kind of implicit feedback.
Oh, I'm not sure we'll get to that one in this class, but what I will say is, like in the case that you're just doing classification rather than regression, we haven't actually built that in the library yet. Maybe somebody this week wants to try adding it. It would only be a small number of lines of code. You basically have to change the activation function to be a sigmoid, and you would have to change the criterion or the loss function to be cross entropy rather than RMSE, and that will give you a classifier rather than a regressor. Those are the only things you'd have to change. So hopefully somebody this week will take up that challenge, and by the time we come back next week, we will have that working. Okay. So I said that we're basically doing a dot product, right? Or a dot product is kind of the vector version, I guess, of this matrix product. So we're basically doing each of these things times each of these things and then add it together. So that's a dot product. So let's just have a look at how we do that in PyTorch. So we can create a tensor in PyTorch just using this little capital T thing. You can just say that's the FastAI version. The full version is torch.from numpy or something. But I've got it set up so you can basically pass in even a list of lists. So this is going to create a torch tensor with 1, 2, 3, 4. And then here's a torch tensor with 2, 2, 10, 10. Okay, so here are 2 torch tensors. I didn't say .CUDA, So they're not on the GPU, they're sitting on the CPU, just FYI. We can multiply them together, right? And so anytime you have a mathematical operator between tensors in NumPy or PyTorch, it will do element-wise, assuming that they're the same dimensionality, which they are. They're both 2 by 2. Okay, and so here we've got 2 by 2 is 4, 3 by 10 is 30, and so forth. Okay, so there's our A times B. So if you think about basically what we want to do here is we want to take okay, so I've got 1 times 2 is 2, 2 times 2 is 4, 2 plus 4 is 6, and so that is actually the dot product between 1, 2 and 2, 4. And then here we've got 3 by 10 is 30, 4 by 10 is 40, 30 and 40 is 70. So in other words, A times B dot sum along the first dimension, so that's summing up the columns, in other words across a row, okay? This thing here is doing the dot product of each of these rows with each of these rows. Does that make sense? And obviously we could do that with you know, some kind of matrix multiplication approach, but I'm trying to really do things with as little special case stuff as possible. Okay, so that's what we're going to use for our dot products from now on. So basically all we need to do now is remember we have the data we have is not in that cross-tab format. So in Excel we've got it in this cross-tab format, but we've got it here in this listed format. User, movie rating, user, movie rating, user, movie rating. So conceptually we want to be like looking up this user into our embedding matrix to find their 50 factors, looking up that movie to find their 50 factors, and then take the dot product of those two 50 long vectors. So let's do that. To do it, we're going to build a layer, our own custom neural net layer. That's not really a neural net, right? So the more generic vocabulary we call this is we're going to build a PyTorch module. Okay? So a PyTorch module is a very specific thing. It's something that you can use as a layer in a neural net. Once you've created your own PyTorch module, you can throw it into a neural net. And a module works by assuming we've already got one, say, called model. You can pass in some things in parentheses and it will calculate it, right? So assuming that we already have a module called dot product, we can instantiate it like so to create our dot product object, and we can basically now treat that like a function, right? But the thing is, it's not just a function, because we'll be able to do things like take derivatives of it, stack them up together into a big stack of neural network layers, blah, 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 right? So it's basically a function that we can kind of compose very conveniently. So here, how do we define a module, which, as you can see here, returns a dot product? Well, we have to create a Python class, right? And so if you haven't done Python OO before, you're going to have to learn, because all PyTorch modules are written in Python OO. And it's one of the things I really like about PyTorch is that it doesn't reinvent totally new ways of doing things like TensorFlow does all the time. In PyTorch, they really tend to use Pythonic ways to do things. So in this case, how do you create some kind of new behavior? You create a Python class.
So, Jeremy, suppose that you have a lot of data, not just a little bit of data you can have in memory. Will you be able to use FastAI to solve collaborative filtering?
Yes, absolutely. It uses mini-batch stochastic gradient descent, which does it a batch at a time. This particular version is going to create a pandas data frame, and a pandas data frame has to live in memory. Having said that, you can get easily 512 gig, instances on Amazon. So like if you had a CSV that was bigger than 512 gig, That would be impressive. If that did happen, I guess you would have to instead save that as a bcolz array and create a slightly different version that reads from a bcolz array to streaming in, or maybe from a Dask data frame, which also, it would be easy to do. I don't think I've seen real world situations where you have 512 gigabyte collaborative filtering matrices, but yeah, we can do it. Okay, now this is PyTorch specific. This next bit is that when you define like the actual work to be done, which is here, return user times movie.sum, you have to put it in a special method called forward. Okay, and this is this idea that like it's very likely you're creating a neural net, right? In a neural net, the thing where you calculate the next set of activations is called the forward pass, and so that's doing a forward calculation. The gradients is called the backward calculation. We don't have to do that because PyTorch calculates that automatically. So we just have to define forward, right? So we create a new class, we define forward, and here we write in our definition of dot product. Okay, so that's it. So now that we've created this class definition, we can instantiate our model, right? And we can call our model and get back the numbers we expected. Okay, so that's it. That's how we create a custom PyTorch layer. And if you compare that to like any other library around, pretty much this is way easier. Basically, I guess because we're leveraging what's already in Python. So let's go ahead and now create a more complex module. And we're going to basically do the same thing. We're going to have a forward again. We're going to have our users times movies.sum. But we're going to do one more thing beforehand, which is we're going to create two embedding matrices. And then we're going to look up our users and our movies in those embedding matrices. So let's go through and do that. So the first thing to realize is that the user IDs and the movie IDs may not be contiguous. Like maybe they start at 1 million and go to 1,001,000, say, right? So if we just used those IDs directly to look up into an embedding matrix, we would have to create an embedding matrix of size 1,001,000, right? Which we don't want to do. So the first thing I do is to get a list of the unique user IDs, and then I create a mapping from every user ID to a contiguous integer. This thing I've done here, where I've created a dictionary which maps from every unique thing to a unique index, is well worth studying during the week because like it's super, super handy. It's something you very, very often have to do in all kinds of machine learning. Right? And so I won't go through it here. It's easy enough to figure out. If you can't figure it out, just ask on the forum. Anyway, so once we've got the mapping from user to a contiguous index, we then can say, let's now replace the user ID column with that contiguous index. Right? So pandas.apply applies an arbitrary function. In Python, lambda is how you create an anonymous function on the fly. And this anonymous function simply returns the index. Do the same thing for movies. And so after that, we now have the same ratings table we had before, but our IDs have been mapped to contiguous integers. And therefore, they're things that we can look up into an embedding matrix. So let's get the count of our users and our movies. And let's now go ahead and try and create our Python version of this. So earlier on, when we created our simplest possible PyTorch module, there was no like state. We didn't need a constructor because we weren't like saying how many users are there or how many movies are there or how many factors do we want or whatever, right? Anytime we want to do something like this, where we're passing in and saying we want to construct our module with this number of users and this number of movies, then we need a constructor for our class. And you create a constructor in Python by defining a dunder init, underscore, underscore, init, underscore, underscore, special name. So this just creates a constructor. Again, if you haven't done OO before, you'll need to do some study during the week, but it's a pretty simple idea. This is just the thing that when we create this object, this is what gets run. Okay. Again, special Python thing, when you create your own constructor, you have to call the parent class constructor, and if you want to have all of the cool behavior of a PyTorch module, you get that by inheriting from nn.module, neural net module. Okay, so basically by inheriting here and calling the superclass constructor, we now have a fully functioning PyTorch layer. Okay, so now we have to give it some behavior, and so we give it some behavior by storing some things in it, right? So here we're going to create something called self.u, u for users, and that is going to be an embedding layer. Number of rows is n users, number of columns is n factors. Right? So that is exactly this, right? The number of rows is n users, the number of columns is n factors. And then we'll have to do the same thing for movies. Right? So that's going to go ahead and create these two randomly initialized arrays. However, when you randomly initialize an array, it's important to randomly initialize it to a reasonable set of numbers, like a reasonable scale. Right? If we randomly initialize them from like 0 to 1,000,000, then we would start out, and these things would start out being like billions and billions of size rating. And that's going to be very hard to do gradient descent on. So I just kind of manually figured here, like, okay, about what size numbers are going to give me about the right ratings. And so we know we need ratings between about 0 and 5. So if we start out with stuff between about 0 and 0.05, then we're going to get ratings of about the right level. You can easily enough back calculate that. In neural nets, there are standard algorithms for basically doing that calculation, and the key algorithm is something called He initialization from Kai-Ming He, and the basic idea is that you take the you basically set the weights equal to a normal distribution with a standard deviation which is basically inversely proportional to the number of things in the previous layer. And so in our previous layer, so in this case we basically, if you basically take that 0 to 0.05 and multiply it by the fact that you've got 40 things, was it 40 or 50 things coming out of it? 50 things coming out of it, then you're going to get something of about the right size. PyTorch already has like her initialization class there. Like we don't normally in real life have to think about this. We can just call the existing initialization functions. But we're trying to do this all like from scratch here, okay, without any special stuff going on. So there's quite a bit of PyTorch notation here. So self.u we've already set to an instance of the embedding class. It has a .weight attribute which contains the actual embedding matrix. So that contains this. The actual embedding matrix is not a tensor, it's a variable. A variable is exactly the same as a tensor. In other words, it supports the exact same operations as a tensor, but it also does automatic differentiation. And that's all a variable is, basically. To pull the tensor out of a variable, you get its data attribute. Okay, so this is now the tensor of the weight matrix of the self.u embedding. And then something that's really handy to know is that all of the tensor functions in PyTorch, you can stick an underscore at the end, and that means do it in place, right? So this is, say, create a uniform random number of an appropriate size for this tensor, and don't return it, but actually fill in that matrix in place. Okay, so that's a super handy thing to know about. I mean, it wouldn't be rocket science otherwise. We would have to have gone okay, there's the non-in-place version. That's what saves us some typing, saves us some screen noise, that's all. Okay, so now we've got our randomly initialized embedding weight matrices. And so now the forward, I'm actually going to use the same columnar model data that we used for Rossmann. And so it's actually going to be passed both categorical variables and continuous variables. And in this case, there are no continuous variables. So I'm just going to grab the 0th column out of the categorical variables and call it users, and the first column and call it movies. Okay, so I'm just kind of too lazy to create my own. I'm not so much too lazy. We do have a special class for this, but I'm trying to avoid creating a special class. So we're just going to leverage this columnar model data class. Okay, so we can basically grab our user and movies mini batches, right? And remember, this is not a single user and a single movie. This is going to be a whole mini batch of them. We can now look up that mini batch of users in our embedding matrix U and the movies in our embedding matrix M. Right? So this is like exactly the same as just doing an array lookup to grab the user ID numbered value, but we're doing it a whole mini batch at a time. Right? And so it's because PyTorch can do a whole mini batch at a time with pretty much everything that we can get really easy speed up. We don't have to write any loops on the whole to do everything through our mini batch. And in fact, if you do ever loop through your mini batch manually, you don't get GPU acceleration. That's really important to know, right? So you never want to have a for loop going through your mini batch. You always want to do things in this kind of like whole mini batch at a time. But pretty much everything in PyTorch does things a whole mini batch at a time, so you shouldn't have to worry about it. And then here's our dot product, just like before. All right? So having defined that, I'm now going to go ahead and say, all right, my x values is everything except the rating and the timestamp in my ratings table. My y is my rating. And then I can just say, okay, let's grab a model data from a data frame using that x and that y. And here is our list of categorical variables. Okay. And then, so let's now instantiate that PyTorch object, right? So we've now created that from scratch. And then the next thing we need to do is to create an optimizer. So this is part of PyTorch. The only fast AI thing here is this line, right? Because like I don't think showing you how to build data sets and data loaders is interesting enough, really. We might do that in part 2 of the course. I mean, it's actually so straightforward, like a lot of you are already doing it on the forums. So I'm not going to show you that in this part. But if you're interested, feel free to talk on the forums about it. But I'm just going to basically take the thing that feeds us data as a given, particularly because these things are so flexible, right? You know, if you've got stuff in a data frame, you can just use this. You don't have to rewrite it. So that's the only fast AI thing we're using. So this is a PyTorch thing. And so Optim is the thing in PyTorch that gives us an optimizer. We'll be learning about that very shortly. So it's actually the thing that's going to update our weights. PyTorch calls them the parameters of the model. So earlier on, we said model equals embedding dot blah, 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 right? And because embedding dot derives from nn.module, we get all of the PyTorch module behavior. And one of the things we got for free is the ability to say dot parameters. So that's pretty handy, right? That's the thing that basically is going to automatically give us a list of all of the weights in our model that have to be updated. And so that's what gets passed to the optimizer. We also pass to the optimizer the learning rate, the weight decay, which we'll talk about later, and momentum, that we'll talk about later. Okay, one other thing that I'm not going to do right now, but we will do later, is to write a training loop. So the training loop is a thing that loops through each mini batch and updates the weight to subtract the gradient times the learning rate. There's a function in FastAI which is the training loop. And it's pretty simple. Here it is, right? For epoch in epochs, this is just the thing that shows a progress bar, so ignore this. For x, y in my training data loader, calculate the loss, print out the loss in our progress bar, call any callbacks you have, and at the end, call the metrics on the validation. Right? So it's just for each epoch, go through each mini batch and do one step of our optimizer. Step is basically going to take advantage of this optimizer, but we'll be writing that from scratch shortly. So notice we're not using a learner. Okay, we're just using a PyTorch module. So this fit thing, although it's part of FastAI, it's like lower down the layers of abstraction now. This is the thing that takes a regular PyTorch model. So if you ever want to like skip as much FastAI stuff as possible, like you've got some PyTorch model, you've got some code on the internet, you basically want to run it, but you don't want to write your own training loop, then this is what you want to do. You want to call FastAI's fit function. And so what you'll find is like the library is designed so that you can kind of dig in at any layer of abstraction you like, right? And so at this layer of abstraction, you're not going to get things like stochastic gradient descent with restarts. You're not going to get like differential learning rates, like all that stuff that's in the learner. Like you could do it, but you'd have to write it all by hand yourself, right? So that's the downside of kind of going down to this level of abstraction. The upside is that, as you saw, the code for this is very simple. It's just a simple training loop. It takes a standard PyTorch model. So this is a good thing for us to use here. We can just call it, and it looks exactly like what we're used to seeing, right? We get our validation and training loss for the 3 epochs. Okay. Now you'll notice that we wanted something around 0.76. So we're not there. So in other words, the default FastAI collaborative filtering algorithm is doing something smarter than this. So we're going to try and do that. One thing that we can do, since we're calling our, this lower level fit function, there's no learning rate annealing, we could do our own learning rate annealing. So you can see here, there's a FastAI function called set learning rates. You can pass in a standard PyTorch optimizer and pass in your new learning rate, and then call fit again. And so this is how we can like manually do a learning rate schedule. And so you can see we've got a little bit better, 1.13. We've still got a long way to go. Okay, so I think what we might do is we might have a 7-minute break, and then we're going to come back and try and improve this score a bit. For those who are interested, somebody was asking me at the break for a kind of a quick walkthrough. So this is totally optional. But if you go into the FastAI library, there's a model.py file. And that's where fit is, which we're just looking at, which goes through each epoch in epochs, and then goes through each x and y in the mini batch, and then it calls this step function. So the step function is here, and you can see the key thing is it calculates the output from the model. The model's called M, right? And so if you remember our dot product, we didn't actually call model.forward, we just called model parentheses. And that's because the nn.module automatically, when you call it as if it's a function, it passes it along to forward. Okay, so that's that's what that's doing there, right? And then the rest of this we'll learn about shortly, which is basically doing the loss function and then the backward pass. Okay, so for those who are interested, that's kind of gives you a bit of a sense of how the code is structured if you want to look at it. And as I say, like the FastAI code is designed to both be world-class performance, but also pretty easy to read. So like, feel free, like take a look at it, and if you want to know what's going on, just ask on the forums. And if you think there's anything that could be clearer, let us know. Because the code is definitely, we're going to be digging into the code more and more. Okay, so let's try and improve this a little bit, and let's start off by improving it in Excel. So you might have noticed here that we've kind of got the idea that user 72, like sci-fi, modern movies with special effects, whatever, and movie number 27 is sci-fi and has special effects and not much dialogue. But we're missing an important piece, which is like, user 72 is pretty enthusiastic on the whole, and on average rates things highly, And movie 27, it's just a popular movie, which just on average it's higher. So what we'd really like is to add a constant for the user and a constant for the movie. And remember, in neural network terms, we call that a bias, right? So we want to add a bias. So we could easily do that, and if we go into the bias tab, here we've got the same data as before, and we've got the same latent factors as before, and I've just got one extra row here and one extra column here, and you won't be surprised to hear that we now take the same matrix multiplication as before, and we add in that, and we add in that. Okay, so that's our bias. So other than that, we've got exactly the same loss function over here. And so just like before, we can now go ahead and solve that. And now our changing variables include the bias. And we can say solve. And if we leave that for a little while, it will come to a better result than we had before. Okay. So that's the first thing we're going to do to improve our model. And there's really very little to show. Just to make the code a bit shorter, I've defined a function called getEmbedding, which takes a number of inputs and a number of factors. So the number of rows in the embedding matrix and the number of columns in the embedding matrix. Creates the embedding and then randomly initializes it. I don't know why I'm doing negative to positive here, and I did 0 last time. Honestly, it doesn't matter much as long as it's in the right ballpark. And then we return that initialized embedding. So now we need not just our users by factors, which I'll chuck into U, our movies by factors, which I'll chuck into M, but we also need users by 1, which we'll put into UB, user bias, and movies by 1, which we'll put into movie bias. Okay, so this is just doing a list comprehension, going through each of the tuples, creating embedding for each of them, and putting them into these things. Okay, so now our forward is exactly the same as before. U times M dot sum. This is actually a little confusing because we're doing it in two steps. Maybe to make it a bit easier, let's pull this out, put it up here, put this in parentheses. Okay, so maybe that looks a little bit more familiar. All right, U times M dot sum, that's the same dot product. And then here we're just going to add in our user bias and our movie bias. Dot squeeze is the PyTorch thing that adds an additional unit axis on. That's not going to make any sense if you haven't done broadcasting before. I'm not going to do broadcasting in this course because we've already done it and we're doing it in the machine learning course. But basically, in short, broadcasting is what happens when you do something like this, where UM is a matrix, UB self.ub users is a vector. How do you add a vector to a matrix? And basically what it does is it duplicates the vector so that it makes it the same size as the matrix. And the particular way, whether it duplicates it across columns or down rows or how it does it, is called broadcasting. The broadcasting rules are the same as NumPy. PyTorch didn't actually used to support broadcasting, so I was actually the guy who first added broadcasting to PyTorch using an ugly hack, and then the PyTorch authors did an awesome job of supporting it actually inside the language. So now you can use the same broadcasting operations in PyTorch as NumPy. If you haven't dealt with this before, it's really important to learn it because it's kind of the most important fundamental way to do computations quickly in NumPy and PyTorch. It's the thing that lets you not have to do loops. Could you imagine here if I had to loop through every row of this matrix and add this vector to every row? It would be slow. It would be a lot more code. And the idea of broadcasting, it actually goes all the way back to APL, which was a language designed in the 50s by an extraordinary guy called Ken Iverson. APL was originally designed or written out as a new type of mathematical notation. He has this great essay called Notation as a Tool for Thought. And the idea was that really good notation could actually make you think of better things. And part of that notation is this idea of broadcasting. I'm incredibly enthusiastic about it, and we're going to use it plenty. So either watch the machine learning lesson or Google NumPy broadcasting for information. Anyway, so basically it works reasonably intuitively. We can add the vectors to the matrix. All right. Having done that, we're now going to do one more trick, which is, I think it was Yannet asked earlier about could we squish the ratings to be between 1 and 5? And the answer is we could, right? And specifically what we could do is we could put it through a sigmoid function. Right? So to remind you, a sigmoid function looks like that, right? And that's 1. Right? We could put it through a sigmoid function, so we could take 4.96 and put it through a sigmoid function, and that, that's kind of high, so it kind of be over here somewhere, right? And then we could multiply that sigmoid, the result of that by 5, for example, right? And in this case, we want it to be between 1 and 5, right? So maybe we'd multiply it by 4 and add 1, for instance. So that's the basic idea. And so here is that trick. We take the result. So the result is basically the thing that comes straight out of the dot product plus the addition of the biases, and put it through a sigmoid function. Now in PyTorch, basically all of the functions you can do to tensors are available inside this thing called capital F. And this is totally standard in PyTorch. It's actually called torch.nn.functional, but everybody, including all of the PyTorch docs, import torch.nn.functional as capital F, right? So capital F.sigmoid means a function called sigmoid that is coming from Torch's functional module, right? And so that's going to apply a sigmoid function to the result. So squish them all between 0 and 1 using that nice little shape. And then I can multiply that by 5 minus 1 equals 4, right? And then add on 1, and that's going to give me something between 1 and 5. Okay? So, there's no need to do this. I could comment it out, and it'll still work, right? But now it has to come up with a set of calculations that are always between 1 and 5, right? Whereas if I leave this in, then it's makes it really easy. It's basically if you think this is a really good movie, just calculate a really high number. If it's a really crappy movie, calculate a really low number, and I'll make sure it's in the right region. So even though this isn't a neural network, it's still a good example of this kind of if you're doing any kind of parameter fitting, try and make it so that the thing that you want your function to return, it's easy for it to return that. Okay, so that's why we do that function squishing. So we call this embedding.bias. So we can create that in the same way as before. You'll see here I'm calling .CUDA to put it on the GPU because we're not using any learner stuff. Normally that'll all happen for you, but we have to manually say put it on the GPU. This is the same as before, create our optimizer, fit exactly the same as before, and these numbers are looking good. Right? And again, we'll do a little change to our learning rate schedule, and we're down to 0.8. So we're actually pretty close. Pretty close. So that's the key steps. And this is how most collaborative filtering is done. And Yannet reminded me of an important point, which is that this is not, strictly speaking, a matrix factorization. Because strictly speaking, a matrix factorization would take that matrix by that matrix to create this matrix. And remembering anywhere that this is empty, like here or here, we're putting in a 0, right? We're saying if the original was empty, put in a 0, right? Now, normally, you can't do that with normal matrix factorization. With normal matrix factorization, it creates the whole matrix. And so it was a real problem, actually, when people used to try and use traditional linear algebra for this, because when you have these sparse matrices, like in practice, this matrix doesn't have many gaps, because we picked the users that watch the most movies and the movies that are the most watched. But if you look at the whole matrix, it's mainly empty. And so traditional techniques treated empty as 0. And so like you basically have to predict a 0 as if the fact that I haven't watched a movie means I don't like the movie. And that gives terrible answers. So this probabilistic matrix factorization approach takes advantage of the fact that our data structure actually looks like this rather than that crosstab, right? And so it's only calculating the loss for the user ID, movie ID combinations that actually appear. Right? So it's actually like user ID 1, movie ID 1029, should be 3, it's actually 3.5, so our loss is 0.5. Like there's nothing here that's ever going to calculate a prediction or a loss for a user-movie combination that doesn't appear in this table. Right? By definition, the only stuff that we can appear in a mini batch is what's in this table. Okay? And like a lot of this happened, interestingly enough, actually in the Netflix prize. So before the Netflix prize came along, this probabilistic matrix factorization, it had actually already been invented, but nobody noticed. Right? And then in the first year of the Netflix prize, someone wrote this like really, really famous blog post where they basically said like, hey, check this out. Incredibly simple technique, works incredibly well, and suddenly all the Netflix leaderboard entries went like much, much better. And so, that's quite a few years ago now, and this is like now every collaborative filtering approach does this. Not every collaborative filtering approach adds this sigmoid thing, by the way. It's not like rocket science. This is not like the NLP thing we saw last week, which is like, hey, this is a new state of the art. Like this is, not particularly uncommon, but there are still people that don't do this. And it definitely helps a lot, right, to have this. And so, actually, what we could do is maybe now's a good time to have a look at the definition of this, right? So the column data module contains all these definitions. And we can now compare this to the thing we originally used, which was whatever came out of collab filter dataset, right? So let's go to collab filter dataset. Here it is. And we called getLearner, right? So we can go down to getLearner. And that created a collab filter learner, passing in the model from getModel. Here's getModel. So it created an embedding.bias. And so here is embedding.bias. And you can see here it is, like it's the same thing. There's the embedding for each of the things. Here's our forward that does the u times I dot sum plus plus sigmoid. So in fact, we have just actually rebuilt what's in the FastAI library, literally. Okay. It's a little shorter and easier because we're taking advantage of the fact that there's a special collaborative filtering data set. So we can actually, we're getting passed in the users and the items, and we don't have to pull them out of cats and consts. But other than that, this is exactly the same. So hopefully you can see, like, the FastAI library is not some inscrutable code containing concepts you can never understand. We've actually just built up this entire thing from scratch ourselves. And so why did we get 0.76 rather than 0.8? You know, I think it's simply because we used stochastic gradient descent with restarts and a cycle multiplier and an atom optimizer. You know, like a few little training tricks. Yes, Unit.
So I'm looking at this and thinking that is we could totally improve this model, but maybe looking at the date and doing some tricks with the date, because this is kind of just a regular kind of model in a way.
Yeah.
You can add more features to
Yeah,
it.
exactly. So like now that you've seen this, you could now, you know, even if you didn't have embedding.bias in a notebook that you've written yourself, but it was some other model that's in FastAI, you could look at it in FastAI and be like, oh, that does most of the things that I'd want to do, but it doesn't deal with time. And so you could just go, oh, okay, let's grab it, copy it, you know, pop it into my notebook, and let's create, you know, the better version, right? And then you can start playing, right? And you can now create your own model class from the open source code here. And so, yeah, Yanette's mentioning a couple of things we could do. We could try incorporating timestamps, so we could assume that maybe, well, maybe there's just like some, for a particular user over time, users tend to get more or less positive about movies. Also, remember there was the list of genres for each movie. Maybe we could incorporate that. So one problem is it's a little bit difficult to incorporate that stuff into this embedding.bias model because it's pretty custom, right? So what we're going to do next is we're going to try to create a neural net version of this, right? So the basic idea here is we're going to take exactly the same thing as we had before. Here's our list of users, right? And here is our embeddings, right? And here's our list of movies, and here is our embeddings, right? And so as you can see, I've just kind of transposed the movie ones so that they're all in the same orientation. And here is our user movie rating, but decross-tabbed, okay? So in the original format. So each row is a user movie rating. Okay. So the first thing I do is I need to replace user 14 with that user's contiguous index, right? And so I can do that in Excel using this match that basically says what, you know, how far down this list do you have to go. And it said user 14 was the first thing in that list, okay? User 29 was the second thing in that list, and so forth, okay? So this is the same as that thing that we did in our Python code where we basically created a dictionary to map this stuff. So now we can, for this particular user movie rating combination, we can look up the appropriate embedding, right? And so you can see here what it's doing is it's saying, all right, let's basically offset from the start of this list. And the number of rows we're going to go down is equal to the user index, and the number of columns we're going to go across is 1, 2, 3, 4, or 5. Okay, and so you can see what it does is it creates 0.19, 0.63, 0.31. Here it is, 0.19, 0.33. Okay, so this is literally what an embedding does. But remember, this is exactly the same as doing a one-hot encoding, right? Because if instead this was a vector containing 1, 0, 0, 0, 0, 0, right, and we multiplied that by this matrix, then the only row it's going to return would be the first one. Okay, so it's really useful to remember that embedding actually just is a matrix product. The only reason it exists, is because this is an optimization. You know, this lets PyTorch know, like, okay, this is just a matrix multiply, but I guarantee you that, you know, this thing is one-hot encoded, and therefore you don't have to actually do the matrix multiply, you can just do a direct lookup. Okay, so that's literally all an embedding is it is a computational performance thing for a particular kind of matrix multiply. All right, so that looks up that user's user, and then we can look up that user's movie. All right, so here is movie ID 417, which apparently is index number 14. Here it is here. So it should have been 0.75.47. Yes, it is 0.75.47. Okay, so we've now got the user embedding and the movie embedding. And rather than doing a dot product of those two, right, which is what we do normally, instead, what if we concatenate the two together into a single vector of length 10, and then feed that into a neural net? Right? And so anytime we've got, you know, a tensor of input activations, or in this case a tensor of, actually this is a tensor of output activations, this is coming out of an embedding layer, we can chuck it in a neural net, because neural nets, we now know, can calculate anything, okay, including, hopefully, collaborative filtering. So let's try that. So here is our embedding net. So this time I have not bothered to create a separate bias, because instead the linear layer in PyTorch already has a bias in it. Right? So when we go nn.linear, right, let's kind of draw this out. So we've got our U matrix, right, and this is the number of users, and this is the number of factors, right, and we've got our M matrix, right, so here's our number of movies, and here's our, again, number of factors, right, and so remember we look up a single user, we look up a single movie, and let's grab them and concatenate them together. Right, so here's like the user part, here's the movie part. Okay. And then let's put that through a matrix product. Right, so that number of rows here is going to have to be the number of users plus the number of movies, right, because that's how long that is. And then the number of columns can be anything we want. Because we're going to take that, so in this case we're going to pick 10 apparently, so let's pick 10. And then we're going to stick that through a ReLU, and then stick that through another matrix, which obviously needs to be of size 10 here, and then the number of columns is of size 1, because we want to predict a single rating. Okay, and so that's our kind of flow chart of what's going on, right? It is a standard, I would call it a one hidden layer neural net. It depends how you think of it. Like there's kind of an embedding layer, but because this is linear and this is linear, the two together is really one linear layer, right? It's just a computational convenience. So it's really got one hidden layer because it's just got one layer before this nonlinear activation, right? So in order to create a linear layer with some number of rows and some number of columns, you just go nn.linear. In the machine learning class this week, we learnt how to create a linear layer from scratch by creating our own weight matrix and our own biases. So if you want to check that out, you can do so there, right? But it's the same basic technique we've already seen. So we create our embeddings, we create our 2 linear layers. That's all the stuff that we need to start with. Really, if I wanted to make this more general, I would have had another parameter here called like num hidden, equals 10, and then this would be a parameter. And then you could like more easily play around with different numbers of activations. So when we say like, okay, in this layer, I'm going to create a layer with this many activations, all I mean, assuming it's a fully connected layer, is my linear layer has how many columns in its weight matrix. That's how many activations it creates. All right, so we grab our users and movies, we put them through our embedding matrix, and then we concatenate them together. Okay, so torch.cat concatenates them together on the first dimension. So in other words, we concatenate the columns together to create longer rows. Okay, so that's concatenating on dimension 1. Dropout we'll come back to in a moment. We've looked at that briefly. So then, having done that, we'll put it through that linear layer we had. We'll do our ReLU, and you'll notice that ReLU is, again, inside our capital F, nn.functional, right? It's just a function. So remember, activation functions are basically things that take one activation in and spit one activation out. In this case, take in something that can have negatives or positives and truncate the negatives to 0. That's all ReLU does. And then here's our sigmoid. So that is now a genuine neural network. I don't know if we get to call it deep. It's only got one hidden layer, but it's definitely a neural network, right? And so we can now construct it. We can put it on the GPU. We can create an optimizer for it, and we can fit it. Right? Now you'll notice there's one other thing I've been passing to fit, which is what loss function are we trying to minimize? Okay, and this is the mean squared error loss. And again, it's inside F. Okay, pretty much all the functions are inside F. Okay, so one of the things that you have to pass fit is something saying like, how do you score this? What counts as good or bad?
So Jeremy, now that we have a real neural net, do we have to use the same number of embeddings for users and...
That's a great question. You don't. No, you're absolutely right. You don't. And so, like, we've got a lot of benefits here, right? Because if we, think about, we're grabbing a user embedding, we're concatenating it with a movie embedding, which maybe is like, I don't know, some different size. But then also, perhaps we looked up the genre of the movie, and like, there's actually a embedding matrix of like number of genres by, I don't know, 3 or something. And so like we could then concatenate like a genre embedding, and then maybe the timestamp is in here as a continuous number, right? And so then that whole thing we can then feed into, our neural net, right? And then at the end, remember, our final nonlinearity was a sigmoid, right? So we can now recognize that this thing we did where we did sigmoid times max rating minus min rating plus blah, 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 is actually just another nonlinear activation function, right? And remember, in our last layer, we used generally different kinds of activation functions. So, as we said, we don't need any activation function at all, right? We could just do that, right? But by not having any nonlinear activation function, we're just making it harder. So that's why we put the sigmoid in there as well. Okay? So we can then fit it in the usual way. And there we go. Interestingly, we actually got a better score than we did with this model. So it'll be interesting to try training this with stochastic gradient descent with restarts and see if it's actually better. Maybe you can play around with the number of hidden layers and the dropout and whatever else and see if you can come up with, get a better answer than 0.76-ish. Okay, so this is like if you were going deep into collaborative filtering at your workplace or whatever, this wouldn't be a bad way to go. I'd start out with oh, okay, here's like a collab filter data set. It's already in FastAI. Get learner. There's not much I can send it. Basically, number of factors is about the only thing that I pass in. I can learn for a while, maybe try a few different approaches, and then you're like, okay, there's that's how I go if I use the defaults. Okay, how do I make it better? And then I'd be digging into the code and saying okay, well, what did Jeremy actually do here? Is this actually what I want? And fiddle around with it. So one of the nice things about the neural net approach is that, as Jeanette mentioned, we can have different numbers of embeddings. We can choose how many hidden, and we can also choose dropout, right? So what we're actually doing is we haven't just got ReLU, but we're also going okay, let's delete a few things at random, right? So that's dropout. Right? So in this case, we were deleting after the first linear layer, 75% of them. Right? And then after the second linear layer, 75% of them. So we can add a whole lot of regularization here. So, it kind of feels like this embedding net, you could change this again. We could have it so that we could pass into the constructor. Well, if we wanted to make it look as much as possible like what we had before, we could pass in P's. P's equals 0.75. 0.75. I'm not sure this is the best API, but it's not terrible. Probably since we've only got exactly 2 layers, we could say P1 equals 0.75. 0.75. P2 equals 0.75. And so then this will be P1. This will be P2, where we go. And if you wanted to go further, you could make it look more like our structured data learner. You could actually have this number of hidden, maybe you could make a list. And so then rather than creating exactly one hidden layer and one output layer, this could be a little loop that creates n hidden layers, each one of the size you want. So this is all stuff you can play with during the week if you want to. And I feel if you've got a much smaller collaborative filtering data set, maybe you'd need more regularization or whatever. If it's a much bigger one, maybe more layers would help. I don't know. I haven't seen much discussion of this kind of neural network approach to collaborative filtering, but I'm not a collaborative filtering expert, so maybe it's around, but yeah, it'd be an interesting thing to try. So the next thing I wanted to do was to talk about the training loop. So what's actually happening inside the training loop? So at the moment, we're basically passing off the actual updating of the weights to PyTorch's optimizer. But what I want to do is understand what that optimizer is actually doing. And I also want to understand what this momentum term is doing. So you'll find we have a spreadsheet called GradDesc, Gradient Descent. And it's kind of designed to be read right to left, worksheet-wise. So the rightmost worksheet is some data, right? And we're going to implement gradient descent in Excel, because obviously everybody wants to do deep learning in Excel, and we've done collaborative filtering in Excel, we've done convolutions in Excel, so now we need SGD in Excel so we can replace Python once and for all. Okay, so let's start by creating some data. right? And so here's, here's some independent, so I've got one column of x's, and one column of y's. And these are actually directly linearly related. So this is random, right? And this one here is equal to x times 2 plus 30. Okay, so let's try and use Excel to take that data and try and learn those parameters. Okay, that's going to be our goal. So let's start with the most basic version of SGD. And so the first thing I'm going to do is I'm going to run a macro so you can see what this looks like. So I'll hit run, and it does 5 epochs. I do another 5 epochs, do another 5 epochs. Okay, so the first one was pretty terrible. It's hard to see, so I'll just delete that first one to get better scaling. All right, so you can see actually it's pretty constantly improving the loss, right? This is the loss per epoch. All right, so how do we do that? So let's reset it. So here is my x's and my y's. And what I do is I start out by assuming some intercept and some slope, right? So this is my randomly initialized weights. So I have randomly initialized them both to 1. You could pick a different random number if you like, but I promise that I randomly picked the number 1 twice. There you go. It was a random number between 1 and 1. So here is my intercept and slope. I'm just going to copy them over here, right? So you can literally see this is just equals C1, here is equals C2. Okay? So I'm going to start with my very first row of data, x equals 14, y equals 58. And my goal is to come up, after I look at this piece of data, I want to come up with a slightly better intercept and a slightly better slope. Okay? So to do that, I need to first of all basically figure out which direction is down. In other words, if I make my intercept a little bit higher or a little bit lower, would it make my error a little bit better or a little bit worse? So let's start out by calculating the error. So to calculate the error, the first thing we need is a prediction. So the prediction is equal to the intercept plus x times slope. Right. So that is our zero hidden layer neural network. Okay. And so here is our error. It's equal to our prediction minus our actual squared. So we could play around with this. I don't want my error to be 1849. I'd like it to be lower. So what if we set the intercept to 1.1? 1849 goes to 1840. Okay, so a higher intercept would be better. Right? What about the slope? If I increase that, it goes from 1849 to 1730. Okay, a higher slope would be better as well. Not surprising, because we know, actually, that they should be 30 and 2. So one way to figure that out, in code, in the spreadsheet, is to do literally what I just did. It's to add a little bit to the intercept and the slope and see what happens. And that's called finding the derivative through finite differencing. Right? And so let's go ahead and do that. So here is the value of my error if I add 0.01 to my intercept. Right? So it's C4 plus 0.01, and then I just put that into my linear function, and then I subtract my actual, all squared. Right? And so that causes my error to go down a bit. Right? So increasing my, which one is that? Increasing C4, increasing the intercept a little bit has caused my error to go down. So what's the derivative? Well, the derivative is equal to how much the dependent variable changed by divided by how much the independent variable changed by, right? And so there it is, right? Our dependent variable changed by that minus that, right? And our independent variable we changed by 0.01. So there is the estimated value of the error dB. Right? So remember, when people are talking about derivatives, this is all they're doing. right, is they're saying, what's this value? But as we make this number smaller and smaller and smaller and smaller, right, as it limits to 0. I'm not smart enough to think in terms of like derivatives and integrals and stuff like that. So whenever I think about this, I always think about, an actual like plus 0.01 divided by 0.01, because like I just find that easier. Just like I never think about probability density functions, I always think about actual probabilities. I like toss a coin, something happens 3 times, blah, blah, blah. So I always think like, remember, it's totally fair to do this because a computer is discrete. It's not continuous. Like a computer can't do anything infinitely small anyway, right? So it's actually got to be calculating things at some level of precision, right? And our brains kind of need that as well. So this is like my version of Geoffrey Hinton's like to visualize things in more than 2 dimensions. You just like say 12 dimensions really quickly while visualizing it in 2 dimensions. This is my equivalent, to think about derivatives, just think about division. And like, although all the mathematicians say, no, you can't do that, you actually can. Like if you think of dx dy as being literally, change in x over change in y, like the division actually, like the calculations still work, like all the time. So, okay, so let's do the same thing now with changing my slope by a little bit. And so here's the same thing, right? And so you can see both of these are negative. Okay, so that's saying if I increase my intercept, my loss goes down. If I increase my slope, my loss goes down, right? And so my derivative of my error with respect to my slope is actually pretty high. And that's not surprising because it's actually, the constant term is just being added, whereas the slope is being multiplied by 14. Okay, now finite differencing is all very well and good, but there's a big problem with finite differencing in high dimensional spaces. And the problem is this, right? And this is like, you don't need to learn how to calculate derivatives or integrals, but you need to learn how to think about them spatially, right? And so remember, we have some vector, very high dimensional vector. It's got like 1 million items in it, right? And it's going through some weight matrix, right, of size like 1 million by size 100,000 or whatever. And it's spitting out something of size 100,000. And so you need to realize like there isn't like a gradient here, but it's like for every one of these things in this vector, right, there's a gradient in every direction, in every part of the output, right? So it actually has not a single gradient number, not even a gradient vector, but a gradient matrix, right? And so this is a lot to calculate, right? I would literally have to like add a little bit to this and see what happens to all of these. Add a little bit to this, see what happens to all of these, right? To fill in one column of this at a time. So that's going to be horrendously slow. Like so that's why, like, if you're ever thinking like, oh, we can just do this with finite differencing, just remember, like, okay, we're dealing with these very high dimensional vectors where, this kind of matrix calculus, like all the concepts are identical, but when you actually draw it out like this, you suddenly realize, like, okay, for each number I could change, there's a whole bunch of numbers that it impacts, and I have this whole matrix of things to compute, right? And so your gradient calculations can take up a lot of memory, and they can take up a lot of time. So we want to find some way to do this more quickly, okay? And it's definitely well worth like spending time kind of studying these ideas of like, the idea of like the gradients, like look up things like Jacobian and Hessian. They're the things that you want to search for to start learning about this. Unfortunately, people normally write about them with, lots of Greek letters and blah blah blahs, right? But there are some nice, intuitive explanations out there, and hopefully you can share them on the forum if you find them, because this is stuff you really need to understand in here. Because you're trying to train something and it's not working properly, and like later on we'll learn how to like look inside PyTorch to like actually get the values of the gradients, and you need to know like, okay, well, how would I like plot the gradients? What would I consider unusual? Like, these are the things that turn you into a really awesome deep learning practitioner, is when you can like debug your problems by like grabbing the gradients and doing histograms of them, and like knowing, that you could like plot that, oh, each layer my average gradient's getting worse, or, bigger, or, whatever. Okay, so the trick to doing this more quickly is to do it analytically rather than through finite differencing. And so analytically is basically, there is a list, you probably all learned it at high school, there is literally a list of rules that for every mathematical function, there's this is the derivative of that function. Right? So you probably remember a few of them. For example, x squared is 2x. Right? And so we actually have here an x squared, so here is our 2 times. Right? Now, the one that I actually want you to know is not any of the individual rules, but I want you to know the chain rule, right? Which is, you've got some function of some function of something. Why is this important? I don't know, that's a linear layer, that's a ReLU, right? And then we can kind of keep going backwards, right? Etc. Right? A neural net is just a function of a function of a function of a function, where the innermost is, it's basically linear, ReLU, linear, ReLU, dot, 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 linear, sigmoid, or softmax. Right? And so it's a function of a function of a function. And so therefore, to calculate the derivative of the weights in your model, the loss of your model with respect to the weights of your model, you're going to need to use the chain rule, and specifically, whatever layer it is that you're up to, like I want to calculate the derivative here, I'm going to need to use all of these ones, because that's the function that's being applied. Right? And that's why they call this backpropagation, because the value of the derivative of that is equal to that derivative. Basically, you can do it like this. You can say, let's call u is this, right? Let's call that u, right? Then it's simply equal to the derivative of that times derivative of that. Right? You just multiply them together. And so that's what backpropagation is. Like, it's not that backpropagation is a new thing for you to learn. It's not a new algorithm. It is literally take the derivative of every one of your layers and multiply them all together. Okay? So, like, it doesn't deserve a new name. Right? Apply the chain rule to my layers. Does not deserve a new name, but it gets one, because us neural networks folk really need to seem as clever as possible. It's really important that everybody else thinks that we are way outside of their capabilities. Right? So the fact that you're here means that we failed, because you guys somehow think that you're capable. Right? So remember, it's really important when you talk to other people that you say backpropagation and rectified linear unit, rather than like multiply the layers gradients or replace negatives with zeros. Okay? So here we are. So I've just gone ahead and grabbed the derivative. Unfortunately, there is no automatic differentiation in Excel yet. So I did the alternative, which is to paste the formulae into Wolfram Alpha, and got back the derivatives. So there's the first derivative, and there's the second derivative analytically. We only have one layer in this tinily small neural network, so we don't have to worry about the chain rule. And we should see that this analytical derivative is pretty close to our estimated derivative from the finite differencing, and indeed it is. right? And we should see that these ones are pretty similar as well, and indeed they are, right? And if you're, back when I implemented my own neural nets 20 years ago, I, had to actually calculate the derivatives, and so I always would had something that would check the derivatives using finite differencing. And so for those poor people that do have to write these things by hand, you'll still see that they have like a finite differencing checker. So if you ever do have to implement a derivative by hand, please make sure that you have a finite differencing checker so that you can test it. All right, so there's our derivatives. So we know that if we increase b, then we're going to get a slightly better loss. So let's increase b by a bit. How much should we increase it by? Well, we'll increase it by some multiple of this, and the multiple we're going to choose is called a learning rate. And so here's our learning rate. So here's 1e neg 4. Okay, so our new value is equal to whatever it was before minus our derivative times our learning rate. Okay, so we've gone from 1 to 1.01. And then a, we've done the same thing, so it's gone from 1 to 1.12. So this is a special kind of mini batch. It's a mini batch of size 1. Okay, so we call this online gradient descent. It just means mini batch of size 1. So then we can go on to the next one. X is 86, y is 202, right? This is my intercept and slope copied across from the last row. Okay, so here's my new y prediction, here's my new error, here are my derivatives, here are my new a and b. Right? So we keep doing that for every mini batch of 1 until eventually we run out at the end of an epoch. Okay? And so then at the end of an epoch, we would grab our intercept and slope and paste them back over here as our new values. There we are. And we can now continue again. Right? So we're now starting with, oopsie daisy, I put them in the wrong spot. They should be paste special transpose values. All right. Okay, so there's our new intercept. There's our new slope. Possibly I got those the wrong way around, but anyway, you get the idea. And then we continue. Okay, so I recorded the world's tiniest macro, which literally just copies the final slope and puts it into the new slope, copies the final intercept, puts it into the new intercept, and does that 5 times. And after each time, it grabs the root mean squared error and pastes it into the next spare area, and that is attached to this run button, and so it's going to go ahead and do that 5 times. Okay? So that's stochastic gradient descent in Excel. So to turn this into a CNN, right, you would just replace this error function, right, and therefore this prediction with the output of that convolutional example spreadsheet. Okay, and that then would be a CNN being trained with SGD. Okay. Now the problem is that you'll see when I run this, it's kind of going very slowly, right? We know that we need to get to a slope of 2 and an intercept of 30, and you can kind of see at this rate, it's going to take a very long time, right? And specifically, it's like it keeps going the same direction. So it's like, come on, take a hint. That's a good direction. So the come on, take a hint, that's a good direction, please keep doing that, but more, is called momentum. Right? So on our next spreadsheet, we're going to implement momentum. Okay. So what momentum does is the same thing. And to simplify this spreadsheet, I've removed the finite differencing columns. Okay. Other than that, this is just the same, right? So we've still got our x's, our y's, our a's and b's, our predictions. Our error is now over here. Okay. and here's our derivatives. Okay. Our new calculation for, let's grab a particular row. Our new calculation here for our new A term, just like before, is it's equal to whatever A was before, minus, okay, now this time I'm not taking the derivative, but I'm minusing some other number times the learning rate. So what's this other number? Okay, so this other number is equal to the derivative times, what's this? K1, 0.02, plus 0.98 times the thing just above it. Okay, so this is a linear interpolation between this row's derivative, or this mini batch's derivative, and whatever direction we went last time. Right? So in other words, keep going the same direction as you were before, right? But update it a little bit, right? And so in our in our Python just before, we had a momentum of 0.9. Okay, so you can see what tends to happen is that our negative kind of gets more and more negative, right? All the way up to like 2000. Whereas with our standard SGD approach, our derivatives are kind of all over the place, right? Sometimes they're 700, sometimes negative 700, positive 100, you know. So this is basically saying like, yeah, if you've been going down for quite a while, keep doing that. Until finally here it's like, okay, that seems to be far enough, so now it's getting less and less and less negative, right? Until we start going positive again. So you can kind of see why it's called momentum. It's like once you start traveling in a particular direction for a particular weight, you kind of, the wheels start spinning, and then once the gradient turns around the other way, it's like, oh, slow down, we've got this kind of momentum, and then finally turn back around, right? So when we do it this way, right, we can do exactly the same thing, right? And after 5 iterations, we're at 89, whereas before, after 5 iterations, we're at 104, right? And after a few more, let's do maybe 15. Okay, so that gets us to 102, whereas here, keeps going, right? So it's a bit better. It's not heaps better. You can still see like these numbers, they're not zipping along, right? But it's definitely an improvement. And it also gives us something else to tune, which is nice. Like, so if this is kind of a well-behaved error surface, right? In other words, like, although it might be bumpy along the way, there's kind of some overall direction. Like imagine you're going down a hill, right? And there's like bumps along it. Right? So the more momentum you get up, you're kind of skipping over the tops, right? So we could say like, okay, let's increase our beta up to 0.98, right? And see if that like allows us to train a little faster. And whoa, look at that. Suddenly went straight to 82, right? So one nice thing about things like momentum is it's like another parameter that you can tune to try and make your model train better. In practice, basically everybody does this. Like you look at any like ImageNet winner or whatever, they all use momentum. Okay, and so back over here, when we said use SGD, that basically means use the basic tab of our Excel spreadsheet. But then momentum equals 0.9 means add in, put a 0.9 over here. Okay. And so that's kind of your like default starting point. So let's keep going and talk about Atom. So Atom is something which I actually was not right. Earlier on in this course, I said we've been using Atom by default. We actually haven't. We've actually been, I noticed we've actually been using SGD with momentum by default. And the reason is that Atom has had, it's much faster, as you'll see, it's much, much faster to learn with. But there's been some problems, which is people haven't been getting quite as good like final answers with Atom as they have with SGD with Momentum. And that's why you'll see like all the, ImageNet winning solutions and so forth, and all the academic papers always use SGD with Momentum and not Atom. Seems to be a particular problem in NLP. People really haven't got Atom working at all well. The good news is this was, it looks like this was solved 2 weeks ago. It turned out that the way people were dealing with a combination of weight decay and Atom had a nasty kind of bug in it, basically. And that's kind of carried through to every single library. And one of our students, Anand Sahar, has actually just completed a prototype of adding this new version of Atom. It's called Atom W into FastAI, and he's confirmed that he's getting the much faster, both the faster performance and also the better accuracy. So hopefully we'll have this Atom W in FastAI, ideally before next week. We'll see how we go, but very, very soon. So it is worth telling you about Atom. So let's talk about it. It's actually incredibly simple. But again, make sure you make it sound really complicated when you tell people so that you can look clever. So here's the same spreadsheet again, right? And here's our randomly selected A and B again. Somehow it's still 1. Here's our prediction. Here's our derivatives. Okay, so now how are we calculating our new A and our new B? You can immediately see it's looking pretty hopeful, because even by like row 10, we're seeing the numbers move a lot more, right? So this is looking pretty encouraging. So how are we calculating this? It's equal to our previous value of B minus J8, okay, so we're going to have to find out what that is, times our learning rate divided by the square root of L8. Okay, so we're going to have to dig in and see what's going on. One thing to notice here is that my learning rate is way higher than it used to be. But then we're dividing it by this big number. Okay, so let's start out by looking and seeing what this J8 thing is. Okay, J8 is identical to what we had before. J8 is equal to the linear interpolation of the derivative and the previous direction. Okay, so that was easy. So one part of Atom is to use momentum in the way we just defined. Okay, the second piece was to divide by square root L8. What is that? Square root L8, okay, is another linear interpolation of something and something else. And specifically, it's a linear interpolation of f8 squared. Okay, it's a linear interpolation of the derivative squared, along with the derivative squared last time. Okay, so in other words, we've got two pieces of momentum going on here. One is calculating the momentum version of the gradient. The other is calculating the momentum version of the gradient squared. And we often refer to this idea as a exponentially weighted moving average. In other words, it's basically equal to the average of this one and the last one and the last one and the last one, but we're like multiplicatively decreasing the previous ones, right? Because we're multiplying it by 0.9 times 0.9 times 0.9 times 0.9. And so you actually see that, for instance, in the FastAI code. If you look at fit, we don't just calculate the average loss, right? Because what I actually want, we certainly don't just report the loss for every mini batch, because that just bounces around so much. So instead I say average loss is equal to whatever the average loss was last time times 0.98 plus the loss this time times 0.02. right? So in other words, the FastAI library, the thing that it's actually, when you do like the learning rate finder or plot loss, it's actually showing you the exponentially weighted moving average of the loss. Okay, so it's like a really handy concept. It appears quite a lot, right? The other handy concept to know about is this idea of like, you've got two numbers. One of them is multiplied by some value. The other is multiplied by 1 minus that value. So this is a linear interpolation of two values. You'll see it all the time. And for some reason, deep learning people nearly always use the value alpha when they do this. So like keep an eye out if you're reading a paper or something and you see like alpha times blah, 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 plus 1 minus alpha times some other blah, 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 right? Immediately, like when people read papers, none of us like read every thing in the equation. We look at it and we go, oh, linear interpolation, right? And like, so something I was just talking to Rachel about yesterday is like whether we could start trying to find like a new way of writing papers where we literally refactor them, right? Like it'd be so much better to have written like linear interpolate blah, 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 comma, blah, 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 right? Because then you don't have to have that pattern recognition, right? But until we convince the world to change how they write papers, this is what you have to do, is you have to look, know what to look for, right? And once you do, suddenly the huge page width formulas aren't bad at all. Like you often notice, like for example, the two things in here, like they might be totally identical, but this might be at time t, and this might be at like time t minus 1 or something, right? Like it's very often these big, ugly formulas turn out to be really, really simple, if only they had refactored them. Okay, so what are we doing with this gradient squared? So what we were doing with the gradient squared is we were taking the square root and then we were adjusting the learning rate by dividing the learning rate by that. Right. Okay, so gradient squared is always positive, right? And we're taking the exponentially moving average of a bunch of things that are always positive, and then we're taking the square root of that, right? So when is this number going to be high? It's going to be particularly high if there's like one big, if the gradient's got a lot of variation, right? So if there's a high variance of gradient, then this g squared thing is going to be a really high number. Whereas if it's like a constant amount, right, it's going to be smaller. Because when you add things that are squared, the squareds like jump out much bigger. Whereas if there wasn't much change, right, then it's not going to be as big. So basically, this number at the bottom here is going to be high if our gradient is changing a lot. Now, what do you want to do if you've got something which is like first negative and then positive and then small and then high, right? Well, you probably want to be more careful, right? You probably don't want to take a big step because you can't really trust it, right? So when the variance of the gradient is high, we're going to divide our learning rate by a big number, right? Whereas if our learning rate is very similar kind of size all the time, then we probably feel pretty good about the step, so we're dividing it by a small amount. Right? And so this is called an adaptive learning rate. Right? And like a lot of people have this confusion about ADAM. I've seen it on the forum actually, where people are like, isn't there some kind of adaptive learning rate where somehow you're like setting different learning rates for different layers or something? And it's like, no, not really. Right? All we're doing is we're just saying like, just keep track of the average of the squareds of the gradients and use that to adjust the learning rate. So there's still one learning rate. Okay, in this case it's 1. Right? But effectively, every parameter at every epoch is being kind of like getting a bigger jump if the gradient's been pretty constant for that weight, and a smaller jump otherwise. Okay, and that's ADAM. That's the entirety of ADAM in Excel, right? So there's now no reason at all why you can't train ImageNet in Excel, because you've got access to all of the pieces you need. And so let's try this out. Run. Okay, that's not bad, right? 5, and we're straight up to 29 and 2, right? So the difference between like standard SGD in this is huge. And basically, the key difference was that it figured out that we need to be, moving this number much faster. Okay, and so it did. And so you can see we've now got like two different parameters. One is kind of the momentum for the gradient piece. The other is the momentum for the gradient squared piece. And I think they're called like, I think there's just a tuple of a beta. I think when you want to change it in PyTorch, there's a thing called beta, which is just a tuple of two numbers that you can change. Can you pass that, please?
Jeremy, so you said I think I understand this concept of, when a gradient it goes up and down, then you're not really sure which direction should go, so you should kind of slow things down, therefore you subtract that gradient from the learning rate. But how do you implement that? How far do you go? I guess maybe I missed something early on. Do you set a number somewhere?
We divide the learning rate divided by the square root of the moving average gradient squared. So that's where we use it.
Oh, I'm sorry. Can you be a little more...
Sure. So D2 is the learning rate, which is 1.
Yeah.
M27 is our moving average of the squared gradients. So we just go D2 divided by square root M27. That's it.
Okay, thanks.
I have one question.
Yeah.
The new method that you just mentioned, which is in the process of getting implemented in
Yes, AdamW. Yeah.
AdamW. How different is it from here?
Okay, let's do that. To understand AdamW, we have to understand weight decay. And maybe we'll learn more about that later. Let's see how we go now with weight decay. So the idea is that when you have lots and lots of parameters, like we do with most of the neural nets we train, you very often have like more parameters than data points, or like regularization becomes important. And we've learnt how to avoid overfitting by using dropout, right, which randomly deletes some activations in the hope that it's going to learn some kind of more resilient set of weights. There's another kind of regularization we can use called weight decay, or L2 regularization, and it's actually comes kind of classic statistical technique. And the idea is that we take our loss function, right? So we take our like error squared loss function, and we add an additional piece to it. Let's add weight decay right now. The additional piece we add is to basically add the square of the weights. So we'd say plus b squared plus a squared. Okay, that is now weight decay, or L2 regularization. And so the idea is that now the loss function wants to keep the weights small, right? Because increasing the weights makes the loss worse. And so it's only going to increase the weights if the loss improves by more than the amount of that penalty. And in fact, to make this weight decay, proper weight decay, we then need some multiplier here, right? So if you remember back in our, here we said weight decay equals WD, 5e neg 4. Okay, so to actually use the same weight decay, I would have to multiply by 0.0005. Right? So that's actually now the same weight decay. So if you have a really high weight decay, then it's going to set all the parameters to 0. So it'll never overfit, right? Because it can't set any parameter to anything, right? And so as you gradually decrease the weight decay, a few more weights can actually be used, right? But the ones that don't help much, it's still going to leave it 0, or close to 0, right? So that's what weight decay is literally to change the loss function to add in this sum of squares of weights times some parameter, some hyperparameter, I should say. The problem is that if you put that into the loss function, as I have here, then it ends up in the moving average of gradients and the moving average of squareds of gradients for Adam, right? And so basically we end up, when there's a lot of variation, we end up decreasing the amount of weight decay, and if there's very little variation, we end up increasing the amount of weight decay. So we end up basically saying penalize parameters, weights that are really high, unless their gradient varies a lot, which is never what we intended, right? That's just not the plan at all. So the trick with Adam W is we basically remove weight decay from here, so it's not in the loss function, it's not in the G, not in the G squared, and we move it so that instead it's added directly to the, when we update with the learning rate, it's added there instead. So in other words, it would be, we would put the weight decay, or actually the gradient of the weight decay in here when we calculate the new A and new B. So it never ends up in our G and G squared. So that was like a super fast description, which will probably only make sense if you listen to it 3 or 4 times on the video and then talk about it on the forum. Yeah, but if you're interested, let me know. And we can also look at Anand's code that's implemented this. And the idea of using weight decay is, it's a really helpful regularizer, because it's basically this way that we can kind of say like, please don't increase any of the weight values unless the improvement in the loss is worth it. And so generally speaking, pretty much all state-of-the-art models have both dropout and weight decay. And I don't claim to know like how to set each one and how much of each to use, other than to say like it's worth trying both. Can I grab the...
To go back to the idea of embeddings, is there any way to interpret the final sort of user embeddings?
Absolutely. We're going to look at that next week. It's super fun. It turns out that we'll learn what some of the worst movies of all time are composited. It's like it's that John Travolta Scientology one. It's like Battleship Earth or something. I think that was like the worst movie of all time, according to our embeddings.
Well, at least we've learned something. Do you have any recommendations for scaling the L2 penalty, or is that kind of based on how wide the nodes, or how many nodes there
are?
No,
I have no suggestion at all. Like I kind of look for like papers or Kaggle competitions or whatever similar and try to set it vaguely the same. It seems like in a particular area, like computer vision object recognition, it's like somewhere between 1e neg 4 or 1e neg 5 seems to work. Actually, in the Adam W paper, the authors point out that with this new approach, it actually becomes like, it seems to be much more stable as to what the right weight decay amounts are. So hopefully now, when we start playing with it, we'll be able to have some definitive recommendations by the time we get to part 2. Yeah. All right, well, that's 9 o'clock. So this week, practice the thing that you're least familiar with. So if it's like Jacobians and Hessians, read about those. If it's broadcasting, read about those. If it's understanding Python 00, read about that. Try and implement your own custom layers, read the fast AI layers, and talk on the forum about anything that you find weird or confusing. All right, see you next week.